Okay, so this is the slide that we finished up with last week. So we are going to go through the rest of the presentation today, and it will hopefully be more straightforward to you, and the material that we are going to cover today will most likely look pretty abstract to you, but it will make a lot more sense when we do the labs and the activities the rest of this week and then next week. So a good nebular theory needs to explain some of the rules or the exceptions to the rules that we see within our solar system. So, you know, why is it that certain planets orbit on a different angle than, let's say, just straight up and down in terms of the tilt of the axis? Why is it that certain moons don't follow the orbital spin direction doesn't follow the spin of their planet that they're orbiting? Why is it that certain planets' orbits are tilted relative to that original disk of planets that were orbiting the sun? So it pretty much all stems from the time period which we refer to as heavy bombardment. And that's when we have a lot of planetesimals that were there before that we no longer see because they actually went through the process of accretion. And if you remember, I stressed it out last time during notes. Accretion is an important term that you need to be familiar with. When we talk about accretion, we talk about the accumulation of matter over time to form larger and larger bodies. So we have this time period where a lot of the planetesimals were going through accretion in which they grew in size. So there was a lot of those collisions that, you know, sometimes actually allowed different planetesimals to travel in different directions. They were kind of propelled in different directions. So we have this explanation for why do we have certain moons orbiting in the opposite direction relative to their planet's rotation. And that's most likely because that moon was captured after the planet was already formed. So like I just mentioned, there may have been a collision where a object was propelled into space and eventually captured by a planet's gravitational pull. That may have caused why Triton is actually revolving in an opposite direction. We have some planets, for example, Uranus, that's really tilted on its axis. So if you think about the Earth's tilt, you know, we're at 23.5 degrees. Uranus is almost at 90 degrees, which means it's pretty much, its axis is pretty much laying on its side, if you could imagine it in those terms, and then the planet is spinning in that direction. That is most likely because of a giant impact with another object that kind of knocked it over to its side. Some planets will rotate much faster than others. And you may ask, well, why is that? Well, it's most likely because of an impact that allowed the planet to actually spin faster. And then the question is, why is Earth's moon so special? Why is it so big, you know, relative to our planet? Because it's pretty significant in size. Well, and that could be explained by the giant impact theory, which pretty much states that there was a Mars-sized planetesimal that collided with Earth early on. And that allowed for a lot of debris to be thrown out into space. But the debris was also kept local to Earth because of Earth's gravitational pull. Eventually, that debris accreted to form the moon that we have today. Okay. So you may ask, okay, well, how do we know the age of our solar system? Because we keep talking about this 4.6 billion years old number, but you may ask, well, how do we know that that's exactly what it is? Well, we do use what's known as radiometric dating. And radiometric dating is possible because of radioactive elements that will go through radioactive decay over time. And so pretty much in very basic terms, when you have a radioactive element, it has extra parts to it within its nucleus. And this is a very simplified explanation. Eventually, that nucleus does not have enough energy to hold that nucleus in place, so that nucleus is going to go through decay. Over time, that decay process is pretty consistent. Okay, so let's say if you have a sample of a radioactive material, it is well known for scientists the rate at which that radioactive material is going to decay. And we use a terminology known as half-lives to explain the decay of radioactive material. Sorry. And we know that there is a specific time frame for a specific element that has that constant decay take place. Now keep in mind that every radioactive element is going to have a different time frame at which it decays. So when we look at this graph here, we have potassium 40 represented on the graph, and the red line shows us the decay of that element. Well, when potassium 40 decays, it doesn't just go away. Okay, it actually will decay into another element, and in the example of potassium, it will decay into argon 40. So as potassium decays, the amount of potassium is decreasing because it is decaying into argon. Now, because potassium is decaying into argon, the volume of argon is going to be increasing over time. And that's important to realize, because when we have a sample of material that's radioactive decay, we can look at the proportion of the radioactive material to the proportion of the material that the radioactive element has decayed into. Knowing these two proportions, we can figure out the age of that sample that we're holding. And I know this is going to probably be fairly confusing at first, but the more we do in terms of labs and activities, the more it is going to solidify for you. So we can look at the proportions of radioactive elements in samples, for example, that come from meteorites, okay, that have fallen on the Earth's surface. We can also utilize material from the asteroids that have been collected. Or, you watched a video that talked about them collecting dust from comets. And they also looked at the proportions of radioactive material to the proportion of the material that the radioactive material had decayed into. Knowing those proportions, we can figure out the age of our sample that we're holding. And consistently, all those materials come back as having the age of 4.6 billion years old. So that's the age of our solar system that has been agreed upon by many scientists. It is well established age of our solar system right now. So like I said, we are going to be doing labs and activities that will help you see that change and that radioactive decay that's being represented by different samples that you're going to be doing and working with. So it will make a lot more sense once we get into it later this week and next week.